Welcome to the solutions to the College Physics Springs and Simple Harmonic Motion problem set, problems number 6 and 7. Let's go ahead and jump in with number 6 here. A 500-gram block is released from rest and slides down a frictionless track that begins 2 meters above the horizontal as shown in the diagram below. At the bottom of the track, where the surface is horizontal, the block strikes and sticks to a light spring with a spring constant of 20 newtons per meter. Find the maximum distance the spring is compressed. The key to this problem is the fact that the track is frictionless. So this is a clue that we probably want to start with conservation of mechanical energy. This will be the initial mechanical energy, the state for the initial mechanical energy here, and this down here will be the final state for the mechanical energy, where the block is slid down and compressed the spring. Well, in what form of mechanical energy is possessed in this system in the initial state? Is it moving? No. It's released from rest. Is the spring stretched or compressed at that spot? No. Is it at a height above a base level in a gravitational field? The answer is yes. So we know we start out with gravitational potential energy. In the final state, is the object moving? The answer is no, because it pushes into the spring until it comes to rest. Is the spring stretched or compressed? The answer is yes, and in fact we're trying to find the distance it is compressed. Is it at a height above a base level in a gravitational field in the final state? The answer is no, because it's reached the base level. We would assign the bottom of this hill to be the base level itself. So we only have one form of mechanical energy at the final state as well, and that's elastic potential. So all the gravitational potential in the initial state becomes the elastic potential in the final state. Next, we write the equations for each of those. Gravitational potential energy would be mgho. The elastic potential energy would be 1/2 kx squared. Any canceling? No. There's no variable in both terms that we would be able to cancel. We go ahead and substitute. We have a 0.5 kilogram mass, 9.81 meters per second squared at a height of 2.00 meters. Equals 1/2 spring constant, given in the problem 20.0 newtons per meter, times x squared. Do the algebra and solve for x. Don't forget to take the square root. And we get 0.990 meters to 3 digits. All right, let's go on to number 7. We have a 3 kilogram object is fastened to a light spring with an intervening cord passing over a pulley as shown in the diagram below. The pulley is frictionless and its inertia may be neglected. The object is released from rest when the spring is unstretched. If the object drops 10 centimeters before stopping, find the spring constant of the spring, and B, the speed of the object when it's 5 centimeters below its starting point. So if it's released from here and falls 10 centimeters, they want the speed when it's halfway, having fallen from rest here. All right, in this problem, they did not give us the height above the floor here, or whatever this is, a table or whatever. So we don't know the height from here to here. Because of that, we're going to establish the spot from which it's dropped as the base level. And this gives unusual circumstance with gravitational potential energy. All right, so follow along here. In A, clearly everything's frictionless here, so we're going to start with conservation of mechanical energy. Let's run through our 3 forms in both initial and final state. Initial state, anything moving? No, dropped from rest. Spring stretched or compressed? No, it's unstretched at this position. Is the object a height above the base level in a gravitational field? No, it is not, because we've established this as the base level. So our initial mechanical energy is 0. All three forms are 0. Final state. Is the object moving? No. It falls 10 centimeters and stops. Is the spring stretched or compressed? Yes. As this falls, it drops 10 centimeters. That means the spring stretches upward 10 centimeters. Is our mass above or below a base level in a gravitational field? And the answer is yes. In this case, the mass loses gravitational potential energy, and then that'll be reflected by the fact that we give it a negative sign here. So our initial mechanical energy is 0, and on our final state, we have a gain in the elastic potential energy, and we have a loss of gravitational potential energy, and that loss is because the mass goes below the base level. We go ahead up and set our equations. 0 equals 1/2 kx squared minus mgh. We go ahead and substitute. The spring constant is what we're looking for. So we have 1/2 k. The spring stretches 10 centimeters, which is 0.10 meters. Don't forget to square. And then we subtract the gravitational potential energy of 3 kilograms times 9.81 meters per second squared times the height that it drops, which is 0.10 meters, again the 10 centimeters. Go ahead and do your algebra, solve for k. And to 3 digits you should get 589 newtons per meter. I believe it comes out to be 588.6, but to 3 digits that would be 589. Alright, in B, they want the speed of the object when it's 5 centimeters below the starting point, which is halfway between here and where it stops when it's dropped. Well, to reevaluate, we're going to use conservation of mechanical energy again, and we still have all three forms in the initial state in the diagram being 0. But in the final state, which is 5 centimeters below the drop point, the spring is stretched 5 centimeters. We have a loss of gravitational potential energy below 5 centimeters below the base level, and our object is moving, so we also have kinetic. So that would be reflected here in our elastic potential energy plus our kinetic energy minus our loss of gravitational potential energy in the problem. We go ahead and substitute. We have our elastic potential is 1/2 588.6 newtons per meter using the non-sig fig value times 5 centimeters 0.05 meters squared, don't forget to square, plus 1/2 3 kilograms times v squared, there's our kinetic energy, minus our 3 kilograms 9.81 meters per second squared, and our drop height of 0.05 meters, again there's your 5 centimeters. So here's our loss of gravitational potential. Go ahead and do the algebra, solve for v, and you should get, how would you do that? You would subtract, or either way, you would add this value to the other side. From that, you would subtract this value for the elastic potential energy, multiply by 2, divide by 3, and take the square root to get the velocity. And you would get 0.700 meters per second. Alright, that'll do it for problems 6 and 7. More practice with this in class tomorrow, as we'll do number 9 together.